Second lecture by Shiraz.
Okay, thank you. Okay, so let's continue. Let me remind you where we left off yesterday. Yesterday we had so just a 2-minute recap. We talked about the structure of the equations of hydrodynamics. The equations of hydrodynamics are the statement of the conservation of, in the simplest case, the statement of the conservation of the energy momentum tensor and the charge current. The variables of hydrodynamics are thermodynamic fields made local, namely a temperature, chemical potential, and a velocity field. And the dynamical content to hydrodynamics, the thing that distinguishes the hydrodynamic equations of one fluid from the hydrodynamic equations from the other, are the constitutive relations, the relations that allow you to express the stress tensor and the charge current as functions of local thermodynamic fields. Okay, we discussed that hydrodynamics was a long wavelength effective theory, and so these constitutive relations are both conveniently as well as conceptually to be thought of in a derivative expansion numbers of derivatives. Okay, at the perfect fluid level, at the constitutive relations with at zeroth order the derivative expansion were just specified completely in terms of thermodynamics, and we wrote those down. The question we set ourselves was to try to understand what the constraints were on general grounds for the constitutive relations at higher orders in the derivative expansion. Okay, so we started by analyzing this question just from symmetry. Okay, we just listed all the, we got rid of two irritating but important complications. The first one being that we had field redefinition ambiguity of the thermodynamic fields at higher than zeroth order. You know, what the thermodynamic fields mean in equilibrium is totally clear. It's unambiguous. There's no field redefinition ambiguity there. But at derivative order, we had field redefinition ambiguity, and that allowed us to set a choice of frame. We decided to adopt the Landau frame, in which pi mu nu, the correction to the perfect fluid stress tensor, was transverse to the velocity, and j mu dis, the correction to the perfect fluid charge current, dotted with the velocity vector was 0. Okay, after having adopted this choice of frame, the specification of the stress tensor and the charge current was a little easier. In order to specify the charge current, we needed to specify, the stress tensor pi mu nu, we needed to specify one tensor and one scalar under the preserved SO3. In order to specify the charge current, we needed to specify one vector. Okay, so then what we did was to list all the vectors and vectors, scalars, and tensors that we could form out of one derivative data. You remember that this one derivative data was one derivative expressions that you could build by acting with derivatives on thermodynamic fields, as well as one derivative expressions you could form from background fields, like the background value of the gauge field, or the background value of the curvatures that describe the background on which the fluid propagates. These two have to be treated on equal footing because they mix under equations of motion. Okay, and we listed not all expressions we could form, but all those expressions that were on-shell inequivalent. Okay, because it would have been an overkill to list those that were equal on any solution to the equations of motion. And the symmetry listing I've recounted here for you. We broke up our data into the data that transformed in different ways under the preserved tangent space SO3. We had data that transformed in the scalar, the vector, the pseudo vector, and the tensor. There was one piece of scalar data that we could choose up to on-shell inequivalence to be the expansion of the fluid, del dot u, sometimes called theta. Okay, there were three pieces of vector data that we could choose to be the Einstein combination. That's the derivative of mu by t minus the electric field, and the derivative of the temperature. Whenever I take a vector like a derivative of the temperature, I always project orthogonal to the velocity. Okay, Then there were two pseudo vectors, the vorticity and the magnetic field, and there was one tensor, which was the shear tensor. Okay, so just on the basis of symmetry, we could write pi mu nu was equal to minus eta sigma mu nu minus zeta times del dot u times p mu nu. And j mu dis was equal to, and I'll use the notation that I will give you the results in later on. So is equal to sigma, the conductivity, times E mu minus T times, this is the projector, T. And this exhausted the parity even possible contributions, but if we allowed violation of parity, we also had the possibility of having zeta omega times omega mu plus zeta b times b mu. Okay, this was what we could say just on the grounds of symmetry, just getting the index structure to match in our Landau gauge. Okay, so that was the first part of yesterday's talk. Then we switched gears. We started asking what looked like a perhaps related but distinct question. We started asking the question, given a field theory on a background metric, so the metric with a time-like killing vector field, so that we wrote that as we started asking the question, what can we say about log z on this theory, as a function of the temperature, the chemical potential of the system. Remember, the temperature of the system and the chemical potential of the system are just numbers. The temperature of the system should be distinguished from the temperature field that the system will attain in equilibrium. Okay, what can we say about the log z as a function of the temperature and chemical potential of the system, where z was defined by e to the trace of e to the power minus beta h plus beta mu q. Okay, and we argued that to first order the derivative expansion, just symmetries fixed this partition function to a large extent. We had d3x e to the power minus sigma by t0, p of e to the power minus sigma t0, comma e to the power minus sigma a0 plus mu 0, where p was the ordinary thermodynamic pressure function for flat space equilibrium. This was the square root g3. That's this, g is this, that three-dimensional metric there. Sorry?
I think you decided to call sigma phi.
I decided to call sigma phi, yes. Ah, yes, I'm sorry about that. And then we talked about one derivative corrections to this. So the one derivative corrections I divided up into W1, let's say invariant, plus W1 anom. Okay, and W1 invariant was equal to, and once again I'll use the notation that I will use to present the results. So is equal to C naught by 2 integral ADA plus T0 squared C1 by 2 integral ADA plus T0 C2 by 2 integral ADA, and W1 anom was equal to C by 2 integral A naught by 3 T naught A dA, which in terms of Kaluza-Klein gauge invariant fields has a more complicated expression, C by 2 A naught by 3 T naught A dA plus integral A naught squared by 6 T naught A dA, where the field theory in question obeyed the covariant anomaly equation, d mu j mu covariant is equal to minus C by 8 star F wedge F, and this A was defined in terms of curly A, so AI is curly AI minus AI times A0, and A0 was the actual gauge field plus the chemical potential plus mu naught. Okay, any questions or comments about this?
I didn't understand. I mean, I'm trying to fit this temperature and the temperature field in context of the example you gave yesterday, that around the Earth the temperature is different at different points. So what do you mean by system temperature in that example?
Yes. So what do I mean by the system temperature? By the system temperature, I mean this. Compute the full entropy of the system. Okay? And differentiate it with respect to the full energy of the system. That gives you the temperature of the system. Okay? Now, this system is composed of many little units, each of which has a distinct local temperature. Okay? But T naught is the temperature of the system defined as I defined it just now. You know, it's like some conglomerate. It has a temperature. If you don't look individually to see what it is, there's some temperature.
There's nothing to do with equilibrium.
Well, I mean, of course, temperature is an equilibrium notion.
But in the example you gave, the temperature stays different, right? I mean, the gas around the Earth.
Yes. So the temperature is so for the gas around the Earth, the local temperature will be given by an integration constant, that's T naught times e to the power minus sigma. T naught will be the temperature of the system defined as I defined. Okay. If I have a little time, I'll try to make this more precise as we go. Yes.
So then, if you convert to the temperature field T of x,
yes,
that you would expand in the derivative expression, yes, T naught would be the first term, or no?
No, because sigma is zero order in derivatives. So even at leading order, even in the perfect fluid expansion, okay, things have different local values of the temperature.
Okay.
Okay. That's how equilibrium is. Equilibrium is characterized by one number, but locally the local temperature is different. But it's that one number that characterizes equilibrium, that integration constant, that's the temperature of the system. Okay, if we have time, I'll make this a little more concrete as we go along. But I'm not sure we'll have time. Okay. Any other questions or comments? Okay, so now our mission for the first part of today's lecture is to put these two things together. What information can I get about this side from studying this side? Okay, now in this listing of fluid data, okay, something that I said yesterday, but I will say again because it's very important, is that at leading order in equilibrium, the temperature field was the following. It was T naught times e to the power minus sigma. The chemical potential field was phi. E to the power minus phi times A0 plus mu 0. And the velocity field was what I'm going to call through the rest of my talks the Kaluza-Klein velocity field, which is just a normalized killing vector. So that's equal to e to the power minus phi times 1, 0, 0, 0. This was the values of the fluid dynamical fields in equilibrium at leading order in the derivative expansion, zeroth order in the derivative expansion. Okay. Now, I'm going to take all these expressions that we've listed on the board and categorize them into two kinds. Those that vanish when evaluated on this leading order configuration and those that don't. Okay? The expressions that vanish when evaluated on an arbitrary equilibrium configuration. Okay? An arbitrary equilibrium configuration I'm going to call dissipative. Okay? That's my name for these things. We will see why it's a good name as we go along. Okay? Expressions that don't vanish, okay, I'm going to call non-dissipative. Okay. So the first question I'm going to ask is how many of these expressions here evaluate to 0 when I plug in this equilibrium configuration on these expressions. In order to answer that, I'm going to give you the results of some algebra that is easy to do, but I won't bother to do here. And that is that if you evaluate sigma mu nu Kaluza-Klein, that is sigma mu nu on the Kaluza-Klein vector field, it turns out to be 0. Okay. If you evaluate del dot u Kaluza-Klein, which is equal to the expansion evaluated on this particular velocity field, that also turns out to be 0. On the other hand, if you evaluate the vorticity, okay, if you evaluate the vorticity on this Kaluza-Klein field, you get that this is equal to the star of f, where f is the two form which is del I a j minus del j a I, and there's a half. Okay, it's a simple matter of algebra to plug in the definitions. Yeah, those of you who are familiar with Kaluza-Klein reductions know this in some language. Okay, to check that these statements are true. Okay. Now, with these results in hand, we can go back to this table. Look, does del dot u evaluated on equilibrium vanish or not? Well, I've just told you it vanishes. So this is 0. On this side, I've listed all those terms that don't vanish in equilibrium. So there's a dash, no scalar that doesn't vanish in equilibrium. Okay? What about the vectors? Well, this term is just a background electric field. It doesn't care whether we're in equilibrium or not. It just evaluates to the derivative of A0 in equilibrium. This term is the projected derivative of the temperature. The temperature was proportional to e to the power minus sigma, so it's the derivative of e to the power minus sigma. It's proportional to the derivative of e to the power derivative of sigma, and is non-zero in equilibrium. However, this combination was chosen precisely because it vanishes in equilibrium. Okay, this combination is the derivative of the chemical potential minus minus the electric field with a particular normalization. Now, you remember that this chemical potential is e to the power minus phi times A0 plus a constant. Dividing by the temperature kills the e to the power minus phi. Taking the derivative then acts only on A0, but that's precisely the electric field. Okay? So this combination was chosen so that it vanishes in equilibrium. It was chosen not by me but by Einstein about 100 years ago, as Subir pointed out yesterday, as a sort of distinguished combination. Okay, so of the three vectors, two do not vanish in equilibrium, one does. Okay, so we've got two non-dissipative and one dissipative vectors. Of the two pseudo vectors, neither of them vanish in equilibrium. When we evaluate them in equilibrium, omega mu turns out to be the star of f, the Kaluza-Klein gauge field, Kaluza-Klein field strength, whereas b mu is of course the star of capital F, the ordinary field strength. Okay, and finally sigma mu nu, as I've told you, vanishes in equilibrium, so there's no non-dissipative tensor. Okay, now why was I interested in distinguishing those quantities that vanish and those that don't in equilibrium? The reason for this is that those quantities that vanish in equilibrium cannot be constrained by a study of equilibrium. Okay? What the values of the coefficients are, multiplying those terms that are 0 in equilibrium, okay, maybe there are constraints when you study dynamical processes about those coefficients, but a study of equilibrium just doesn't see those coefficients because they vanish in equilibrium. However, those coefficients that are non-zero in equilibrium can be constrained by the study of equilibrium. Okay, I'm now going to try to argue that all of these quantities, all quantities that have been written in blue that do not vanish in equilibrium, so 2 vectors and 2 pseudo vectors, the coefficients of these quantities are all completely determined by the data in the action, that is in terms of the thermodynamic pressure P and these 4 numbers C0, C1, C2 and C. Okay? And the argument is very simple. The argument is very simple and it goes as follows. Look, given the action here, I can, I have the action as a function of background, the background metric and the background gauge potentials. So I can use it to compute T mu nu on equilibrium and to compute J mu on equilibrium. Okay, just in the usual way, by taking the action and varying it with respect to the metric to get T mu nu, or taking the action and varying it with respect to A mu to get J mu. Okay, this gives us the expressions for what T mu nu is in equilibrium. Okay, now how much data do I have? So I've got T mu nu in equilibrium, and it's expressed. If I do this exercise, I get an answer. Now I'm going to take this answer and break it up into symmetry channels. Okay, so what are the symmetry channels that appear in T mu nu? Now it's important to realize that T mu nu, coming from this equilibrium partition function, doesn't know anything about the Landau gauge condition. So you have all the components of T mu nu. So how many components of T mu nu do you have? Well, in order to see that, look at a 4 cross 4 matrix. It's a 3 cross 3 matrix, which has a trace part and a tensor part. So that's a 5 plus 1. It also has a vector. This is equal to this, so plus 3 plus an additional 1. Okay, so the data in T mu nu is a tensor, a vector, and 2 scalars. So you get 1 tensor, 1 vector, and 2 scalars. Okay, by doing this exercise, by taking this partition function, varying with respect to the metric, and computing T mu nu. Similarly, when you do this exercise of computing J mu, you get a vector and a scalar. Okay, this is the value of the stress tensor for our fluid dynamical field and the value of the charge current for our fluid dynamical field in equilibrium. It's most general possible allowed values. Now, as long as everything here was slowly varying, the sigma field, the phi field, the A0 field, the curvatures and the metric were all slowly varying, this equilibrium configuration should be reconstructed from fluid dynamics. Namely, there should be a solution of the equations of fluid dynamics, okay, which reproduces these values of the stress tensor and the charge current. Okay, so what can the solution of fluid dynamics be? We know what it is at leading order, so T must be equal to T0 e to the power minus phi plus delta T, where delta T is some first order correction to the leading order equilibrium configuration. Similarly, mu must be equal to e to the power minus phi A0 plus mu 0 plus delta mu, and u mu has to be e to the power minus phi 1 0 0 0 plus delta u mu. Okay, now this expression here is a scalar, this expression here is a scalar, and this expression here is a vector. What? Move the board. Okay, so while we don't yet know what delta t, delta mu, and delta u mu is, just from symmetries, we can write it as an expansion in terms of the most general scalars that exist in equilibrium. the most general scalars that exist in equilibrium, the most general vector that exists in equilibrium. Okay? In order to find these scalars and vectors, we just have to look here. There are no one derivative scalars in equilibrium. No gauge invariant one derivative scalars in equilibrium. Okay? There are two gauge invariant one derivative vectors in equilibrium and two gauge invariant one derivative pseudo vectors in equilibrium. Okay? So, just from symmetry, we immediately conclude that delta t, the correction to the equilibrium configuration, has to be 0. Delta mu has to be equal to 0, but delta u mu could be equal to some arbitrary coefficients times these two quantities, some other arbitrary coefficients times these two quantities. Okay, so let's say a1 times del alpha a0 plus a2 times del alpha e to the power minus phi plus p1 times star f plus p2 times star f. Okay? Moreover, we don't yet know the constitutive relations of fluid dynamics to first order. Okay? As I've argued, the constitutive relations multiplying dissipative terms, those that vanish in equilibrium, are irrelevant. They don't contribute to this order. They don't contribute to what we're going to see comparing with equilibrium. But the constitutive relations multiplying those terms that don't vanish in equilibrium, of course, are important. Okay? Now, in the constitutive relations, what did we have? We had pi mu nu that had a 5 and a 1. Okay? But there's no 5 and there's no 1 that's non-vanishing in equilibrium. So as far as the comparison with equilibrium goes, we can ignore the corrections to pi mu nu. Yes?
Why you added those two pseudo vectors?
Allowing for the possibility that our system does not preserve parity.
Wouldn't that mess up the transformation properties of delta?
It would not mess up the SO3 transformation properties. It would mess up the O3 transformation properties. So if our system preserves parity, then we don't allow those additional terms. But if our system violates parity, we do. Yes. Okay? On the other hand, J mu, remember, was a 3, and so that the most general correction to the constitutive relation is in terms of the numbers that multiply this and this, which are actually this and this, and the numbers that multiply this and this, which are actually this and this. Okay? So we have 4 unknown coefficients. We have 4 unknown coefficients here. Okay? The coefficients that multiply these two non-dissipative terms and the coefficients that multiply these two pseudo non-dissipative terms, the parity odd non-dissipative terms. Okay? And now we just equate. We take the expressions that we get from the from the stress tensor obtained by varying the action with respect to the metric, and from the charge current obtained varying the action with respect to the metric, and equate it to what you get from fluid dynamics in terms of the unknown coefficients multiplying these two terms and these two terms, and the unknown corrections to the velocity field. Okay? How many equations did we have? You see, the stress tensor had a 5, a 1, a 3, and a 1. But the equations in the 5 and the 1 are empty, because there are just no 5s and no 1s that are non-vanishing in equilibrium. So, but the 3 was non-empty. Similarly, the charge current had a 3 and a 1. The equation in the 1 was empty, but the equation in the 3 was non-empty. So we have 2 vector equations, each of which determines 4 constants, because there are 4 possible terms that could appear in a vector. These 4. Okay, so the charge current, for instance, the charge current, if you evaluate it by differentiating with respect to the action, is something times this plus something times this plus something times this plus something times this. When you plug into hydrodynamics, you also get something else times the first plus something else times the second, blah blah blah. Equate all the coefficients independently. Do the same thing for the stress tensor. So the important point is that you have as many equations as variables. Okay, you had two unknown vectors. The first unknown vector was the unknown vector in the velocity, correction to the velocity. The second unknown vector was the unknown vector in the correction to the constitutive relation for the charge current. And you have two vector equations, the vector equation coming from T mu nu and the vector equation coming from J mu. These two equations, so there are as many equations as variables. In this case, 8 equations, 8 variables, because each vector can be expanded in a basis of 4 vector fields. Okay? So just by doing the simple algebraic procedure and solving simple algebraic equations, you determine both the correction to the velocity configuration in equilibrium and all coefficients multiplying non-dissipative terms in hydrodynamics. Is this clear? Okay. Is this clear? It's very simple and it's very important. Let me say it again. You see, I've said it in the context of this simple example, which maybe makes it more confusing than when you say it in general. Look, in general, we've seen that the degrees of freedom here in the stress tensor are 5, a 1, a 3, a 1, a 3, and a 1. Okay, so this is the net number of equations we'll have. How many variables will we have? Well, the number of variables we will have is a 3 plus 1 plus 1 in corrections to the equilibrium solution. The temperature, the chemical potential, and the velocity. Plus the 5 plus 1 in the constitutive relations of pi mu nu, plus the 3 in the constitutive relations for J mu. So these are the variables, these are the equations. And you can check that they're the same. 1 5, 2 3s, 3 1s. So in this particular case, we use the fact that there were no scalar terms, no tensor terms, that didn't matter. This procedure is very general. Every non-dissipative term in the constitutive relations is completely determined by the data in your action. The bonus is you also find the corrections to equilibrium. Equilibrium isn't just given by this redshift, the simple redshift factor, that's true at leading order, but it's corrected order by order in the derivative expansion, and this procedure determines the corrections to equilibrium as well as determining every non-dissipative term in the constitutive relations. Now, I'm going to present the results in just 1 minute, but before that you might wonder, well, what you've done is to find some configuration of fluid dynamics that agrees with what you wanted from your action. How do I know it's a solution to the equation of motion of fluid dynamics? That is automatic. Can somebody tell me why it's automatic? Because the equations of motion of fluid dynamics are simply the conservation of the stress tensor and the charge current. But we have chosen our solution so that the stress tensor agrees with what you get by differentiating an action with respect to the metric. You've chosen everything so that the fluid dynamic charge current agrees with what you get by differentiating the action with respect to A mu. But it's automatic that any generally covariant action and any gauge invariant action, when differentiated with respect to the metric and the charge current, will give you a conserved stress tensor and a charge current. So this procedure automatically gives you an equilibrium solution to hydrodynamics that obeys the equations of motion hydrodynamics. But it only works when the non-dissipative terms in the expansion are chosen to be something particular. Okay, now the rest is algebra. Please.
So you did this great trick of fixing what you could have because of the things which didn't vanish at equilibrium. But aren't I always free to add the things which vanish at equilibrium?
Yes.
To the stuff.
Yes, you are. So those terms, the coefficients of those terms that vanish at equilibrium, are unconstrained by my procedure. This procedure does not completely determine the constitutive relations of hydrodynamics, but it determines those parts of it that are non-dissipative. That is, that multiply terms that don't vanish in equilibrium. Okay, exactly. So now let me just present our, the rest is simple algebra. The algebra is as simple as solving 8 equations, 8 linear equations for 8 variables, algebraic equations, no differential equations. Like that, just solve. It's a simple job, and this is what you get. The result may seem a little complicated at first.
Sorry, one more thing.
Please.
You agreed to include anomalies when you had the gauge thing.
Yes.
But you said because you've got an action, stress energy tensors conserve, but couldn't I have gravitational anomalies where it wouldn't?
Yes, you could have a gravitational anomaly, but I'm working so far only to first order in the derivative expansion. Okay, a gravitational anomaly would appear at higher order. Okay, there are many very interesting questions. Where's the expert here? He was here yesterday. I can't remember his name. But, I don't see him here. The guy who speculated on the connection between the C1, C2 and the mixed gauge gravitational anomaly. Okay, he's not here today, but there are many very interesting questions about what you ask, but they are as yet unresolved. Okay, but we don't need to worry about them in the first order in the derivative expansion. Okay, okay, excellent. So let me now tell you about, when you implement this procedure, let me tell you what you get. Okay, you find that alpha 1 is equal to alpha 2 is equal to 0. That is, the term multiplying E mu and the term multiplying the projected derivative of temperature must vanish. Okay? More interestingly, however, you find that zeta omega and zeta b are not equal to 0, but are given by interesting and complicated expressions. It's given by c mu by mu squared 1 minus 2 q by 3 into epsilon plus p mu plus t squared into 4 mu by t minus 2 times c0 plus 2c2 minus qt by epsilon plus p 4 mu by t, the whole thing square, c0 minus 4 mu by t c2 plus 4 c1. Okay, and this is equal to c mu into 1 minus q mu by 2 epsilon plus p. I'm sorry, I called epsilon rho yesterday. Epsilon is the energy density. Okay, I'm sorry for this switch in notation.
These were the coefficients of B and the vorticity?
Exactly. They're listed up there. Zeta omega. Yes. Plus t 2c naught minus q t by epsilon plus p 2 mu by t c0 minus c2. Okay, it doesn't look very illuminating, but it's an explicit expression giving you explicit functions of temperature and chemical potential that can appear in terms of 4 unknown constants. So these non-dissipative coefficients are not set to 0, not necessarily set to 0. In fact, cannot be 0 if C is non-zero. if the system has an anomaly, then it cannot be 0. Whether or not the system has an anomaly, it could be non-zero, but it could be non-zero only in this particular functional form. This particular function is chosen out by our consistency constraint. Okay, and in terms of these 4 constants, this is the most general set of non-dissipative terms that you could have in your hydrodynamic equations. Our considerations have said nothing about the dissipative terms. Let's remember what the dissipative terms are. The dissipative terms are the shear viscosity, the bulk viscosity, and the conductivity. These are completely unconstrained by our considerations precisely because they multiply terms that vanish in equilibrium. Okay? Fine. Now, I should mention that this result was not, in special cases, was not first obtained by us. It was obtained by Sohn and Soroka in a very famous paper that they wrote 2 years ago by a completely different method, the method of entropy positivity, which we will soon turn to in now. Yes?
Can you obtain non-dissipative terms like the classical Hall conductivity or the classical Hall viscosity in your formulation?
Yes, the classical Hall conductivity or the classical. So this is a 2 plus 1 dimensional object. Okay, so I'm not familiar with the names, but for 2 plus 1 dimension, in our paper we've also worked out the case of 2 plus 1 dimensional charge fluid dynamics in the presence of an arbitrary electric and magnetic field, allowing for parity violation, and we've obtained all non-dissipative terms there as well, in terms of action data. So I suspect the answer is yes, but I'm ashamed to say that if you ask me what the Hall conductivity or viscosity was, I'm not sure I would be able to answer that. So I suspect the answer is yes, but I don't know what those names are.
In 2 plus 1 dimension, you allow magnetic field orthogonal to the plane.
Orthogonal to the, you allow B12 in the plane of.
But how about B3 perpendicular to the plane? That's also allowed.
B3, which is B12 in the plane, right?
Yes, yeah.
Yes, we allow that. Yes. Okay. So I suspect the answer is yes, but I would have to talk to you about it. Yes, please.
Is there an easy way to see why alpha 1 and alpha 2 are 0?
Is there an easy way to see why alpha 1 and alpha 2 are 0? Yes, there's an easy way to see why alpha 1 and alpha 2 are 0. And the easy way is this. Look, the full change in the action, the full first derivative correction to the action is parity odd. You see, we got all our fun by equating things that came from the correction of the action to equating corrections in hydrodynamics. But we can grade these equations by parity. Because the corrections to the actions were all parity odd, they all involved an epsilon tensor, they could only have turned on parity odd transport coefficients. So these alpha 1 and alpha 2, since they were parity even, you can see right from the beginning that they have to be 0. In a similar way, we've evaluated the correction to the velocity field in equilibrium. These two terms are, as you would expect right from the beginning, 0, but these two terms are not. Okay, thank you. Other questions, comments? Okay, excellent. Now, for most of the rest of my lecture, what I want to turn to is the second fascinating method based on the principle of entropy increase pioneered by Landau and friends. But before that, I'll just very quickly, just to give you a feeling that this has been worked out in many different examples. I'll very quickly tell you about what happens when you, in just 2 minutes, just the numbers, when you study uncharged at second order. As I have tried to emphasize, my interest in hydrodynamics is as a theoretical subject. It's not terribly important to me whether somebody is really interested in the 27th order and the hydrodynamic expansion or not, but I want to know how in principle I can constrain it to all orders, like a theorist should. So, so just to check that all of this is working and working well, we worked out this exercise for uncharged hydrodynamics to second order in the derivative expansion. We've actually also worked it out for charged hydrodynamics at second order largely, but I'm stressing this uncharged case because there's something to compare to as we will see. Okay, I'm just going to give you the numbers here. Okay, And there's one new feature that happens. You see, firstly, when you work out the symmetry expansion, it turns out that pi mu nu, okay, can be expanded in terms of 15 transport coefficients, each of which is an unknown function of, in this case, just the temperature. It turns out that 7 of these are dissipative, and so unconstrained by our considerations. The remaining 8 are non-dissipative, so are going to be constrained by what we do. Now, our constraining procedure, as I've explained, uses this equilibrium action. Now you can ask, what is the most general form of the equilibrium action at second order in the derivative expansion? And okay, these numbers, I'm assuming parity invariance in what I'm telling you here. We worked it out for the parity odd case as well, but I'm just giving you the parity even answer. It's easy to see that the most general log z, just by symmetries, is the perfect part plus the second order correction, which is a term proportional to del sigma, the whole thing squared, times f1 of sigma, plus a term proportional to the curvature times f2 of sigma, plus a term proportional to 3 of sigma times fij, where fij is the Kaluza-Klein field strength. Okay. In fact, there is one additional second order scalar you can write down, namely del squared of sigma, but that doesn't contribute to the action because del I f of sigma del I of sigma, is a total derivative, so it doesn't make any contribution to the action. So the fact that del squared and any coefficient multiplying del squared can be put into a total derivative form plus something of the form we've already written ensures that it doesn't make any interesting contribution to the action. Okay? So unlike in the case of the first order fluid, the action here is not completely determined in terms of numbers. It's determined in terms of 3 unknown functions of sigma. But there are 8 non-dissipative coefficients that we determine by this process. So what our procedure gives us is an expression for these 8 non-dissipative coefficients as functions of 3 unknown functions. In other words, it gives us 5 relations between these 8 unknown dissipative non-dissipative transport coefficients. The expressions for these 8 unknown non-dissipative transport coefficients in terms of these 3 unknown functions in the action are simple algebraic expressions. There are no derivatives of f1, f2, f3 in the expressions for these 8 transport coefficients. However, if you try to eliminate f1, f2, f3, okay, if you try to eliminate f1, f2, f3 to find relations between these transport coefficients, that elimination process introduces derivatives and gives you a set of 5 differential relations between these 8 otherwise unknown functions. Okay? So it's a more elaborate structure here, but once again the message goes through, that is, you get new constraints on the hydrodynamic expansion, in this case determining 5 out of 8 functions, roughly speaking, okay, from this way of thinking. Okay, we've also worked out this problem in 2 + 1 dimensions, allowing for parity odd fluid dynamics of first order in the derivative expansion. My collaborators worked out the 1 + 1 dimensional case, in which case there's an interesting kind of anomaly, interesting addition to the action. You can work it out in many cases, and you get what you get. Okay, so this is the first class of constraints that significantly cut down on the freedom in the constitutive relations of hydrodynamics. Before we move on to the other constraint, I'll just remind you of the physical principle involved here. There are 2 constraints. Firstly, you demand that in every situation in which equilibrium must exist, the hydrodynamic equations allow for an equilibrium solution. Secondly, this equilibrium solution has a stress tensor and a charge current. Not every stress tensor and charge current is obtained by differentiating an action. Secondly, you demand that the value of the stress tensor and the charge current are such so that they come from derivatives of an action. They obey the integrability conditions for this demand. Okay? These two constraints together give you significant restraints on the hydrodynamic expansion, allow terms in the hydrodynamic expansion. They only constrain non-dissipative terms. Okay? So that's it for this approach. The next half an hour will be on the entropy increase approach. Any questions or comments before we proceed? Please.
The fact that you get the same result as sun using entropy production implies that GR knows about entropy or encodes entropy production.
Yes, GR does encode entropy production.
Is there an easy way to see it?
Yes, it's the Hawking area increase theorem. I will explain this in my last 2 lectures when we turn to the connection with GR. Yes, but the answer is yes. Yes.
So how about constraints like sigma has to be greater than 0 and so on?
That is not obtained from this procedure because we are only looking at equilibrium processes.
What if you look at near equilibrium and the vanity relaxation?
Yeah. I think we could get it, but we haven't done that yet. Yes, right, yes. But for what I've done so far, that's not obtained. Actually, we're working on the first order and time derivatives at the moment. So that could lead to many things. Okay. Other questions or comments?
I have a very simple question. So you are studying all the time everything which is for equilibrium system.
So far, yes, sir.
So in that case, would you set the rest of the coefficients to 0?
No, the rest of the coefficients are just unconstrained.
Would they should be set to 0? Because
no, they shouldn't be set. The other coefficients are like the viscosity, which we know should not be set to 0. As Subir implied, the actual constraints on these other coefficients are not equalities but inequalities. You know, as we will see that as far as we understand, there are 2 kinds of constraints on the coefficients in constitutive relations. Some are sharp equalities that cut down the number of functions involved in your game, and with the other coefficients are constrained by inequalities. This method appears to get all the equalities, but so far is blind to the inequalities. Turning on some small time derivatives may help that. Okay? So the other coefficients are, by our method, completely unconstrained. We know that in actual practice they must be constrained by inequalities. Unitarity, for instance, will imply some of these inequalities. There are many ways of trying to get these inequalities, but this method does not get them. Good. Other questions, comments?
Do alphas get corrections in the second order?
Do what?
Alpha 1 and alpha 2?
Alpha 1 and alpha 2? No, alpha 1 and alpha 2 are coefficients of first order terms. So the fact that they vanish is not going to be corrected at any order, any higher order. Okay? What is true is that parity even coefficients will get non-zero values at second order. In fact, that's what in the uncharged case, that's what I try to indicate here. The parity even coefficients, there are 8 of them, and they're not all 0 because we've got a parity even action. In fact, at second order of uncharged fluids, something interesting happens. All parity odd coefficients, I didn't give you the counting for that, but once you include parity odd terms, turns out that there are 5 additional transport coefficients, 3 of which are non-dissipative. And those 3 non-dissipative parity odd coefficients are automatically just set to 0, because just by symmetry, the most general addition to the action is parity even. It's the converse of what happened previously. Okay? Yes. Any other questions or comments? Okay. So now let's move on. Okay. So I'm now going to tell you about a second method that is that was employed to great effect, but not always completely correctly, by Landau and Lifshitz, and by people subsequently. Okay, and that gets, and tell you about the relationship of what you get by using that method and this method. Okay, so this was a method of trying to constrain the hydrodynamic expansion in a seemingly completely different way. And the method that they employed was to say, look, Hydrodynamics, by its very nature, is a thermal theory. It's a local version of a thermal theory. And there is a fundamental principle that governs thermal physics, namely the principle that entropy always increases and never decreases. Okay? Now, hydrodynamics is thermodynamics made local. So, presumably it should go with a local form of the second law of thermodynamics. How will you write down the local form of the second law of thermodynamics? One way of doing it is to assert the following: that there exists an entropy current, J mu s, such that in every conceivable fluid flow, on every conceivable background, del mu J mu s is greater than or equal to 0. So that locally, in any local region, entropy is always produced and never destroyed. Now, if I want to try to make this statement a little more precise, I have to start thinking about what I mean. What exactly do I mean by this entropy current? You might think at first that what I should mean is the entropy density times u mu. But that's too limited. You see, this is the form of the entropy current. This is the form of the entropy current in equilibrium. But if we are looking at processes at, let's say, first order in the derivative expansion, this expression could be corrected. This is something that Landau and Lifshitz, of course, realized, and they came up with a brilliant ansatz for the correction to this entropy current.
Lifshitz in the book, or was it Lifshitz and Petevsky, or was it some paper?
I don't know. I've only read it from the book. Okay. I should say the work reviewed in Landau and Lifshitz. I should know better. Okay.
Well, if you give so few references that it's hard to figure out.
Yes, exactly. Just in this context, I probably don't have the time to talk about superfluidity, but I just, superfluid hydrodynamics was worked out. The perfect fluid version of superfluid hydrodynamics is sometimes called the Landau-Tisa theory. Equations were written first by Tisa and then by Landau a couple of years later. This is the reference that Landau and Lifshitz give in their book, slightly paraphrased. I make it a bit funnier than it is, but they say these equations were worked out by L. Landau. They were also independently worked out by Tisa, but he didn't understand them. It's almost that. Okay. Yeah, right. Landau and Lifshitz don't give too many references. Okay.
But some of those books were not written by that.
Really? But fluid dynamics was.
It was, okay.
Yes. In fact, the Lifshitz in his introduction says Landau gave this book part of his soul. Yes. Okay. So now, these guys came up with a brilliant suggestion for what the corrected first order entropy what the first order correction to the entropy current should be. Their suggestion was that at first order, J mu s should be s times u mu minus 1 by t times u mu pi mu nu minus mu by t times J mu this. Actually, they give a suggestion in a particular frame, namely the Landau frame, but we've taken this expression and made it gauge invariant, frame invariant. Okay, this is the frame invariant version of their suggestion. And roughly the reasoning is, look, there are two sources of carrying entropy. Stuff that carries entropy moves, that carries entropy. But also heat transfer carries entropy. Okay, dq by t. And this expression here is dq by t. Okay, and then this is needed to make it frame invariant. That is, this would be dq by t in a frame in which the charge current was at rest, in the Eckhart frame. But this would be dq by t in the frame in which energy density was at rest. This is the frame invariant version of that.
What's the last term?
It's minus mu by t, J mu this. Okay? And okay, now what Landau and Lifshitz did was to work out the work reviewed in Landau and Lifshitz, what it did was to work out what the divergence of this entropy current is. Okay, and by using the equations of thermodynamics and the equations of hydrodynamics, the conservation of the stress tense and the conservation of current, assuming that the current is conserved without an anomaly, this will turn out to be important later on. It is not difficult to show that d mu j mu s is equal to this again has been worked out in an arbitrary frame, okay, not necessarily the Landau frame. If you specialize this result to the Landau frame, it becomes a little simpler, because the derivative here acting on the temperature gives you 0, because it gives you u dot pi, and that's 0. Okay, if you specialize so the derivative is only allowed to act on u mu. Since it's multiplying a symmetric object, you can replace this by symmetric derivatives of u. Okay, now the symmetric derivatives of u are the shear tensor and the expansion times p mu nu. So up to numbers which are easy to work out, but I won't bother. This is sigma mu nu pi mu nu by t plus number times theta times pi mu nu p mu nu pi mu nu minus del mu of mu by t minus f mu nu u nu by t j mu this.
How do your u nu indices figure out?
Okay, is this good question. Good question. This derivative acts only on that. Thank you. Okay. Okay. Now, sticking to non-anomalous parity even flows, though it wasn't really on their mind. Okay, so this is what Landau Lifshitz then went on to assert. Okay, they said, now look, this is the entropy current of our system. Okay, this is the entropy current of our system, but it must be positive definite in any fluid flow. Now, let's look. You see this pi mu nu times p mu nu and j mu dis are all expressions of first order in the derivative expansion. Okay, they're being multiplied by explicit expressions which are also of first order in the derivative expansion. Okay, so what we have here on the right hand side is a quadratic form in first order data. The positivity of entropy production is simply the statement that this quadratic form must be positive definite. How do we make such a quadratic form positive definite? Well, you see, this quadratic form can be broken up by symmetry. There's one tensor term in the quadratic form, so the only thing that pi mu nu could have been a sigma mu nu if you look at our table. So it's just that pi mu nu is a coefficient times sigma mu nu, and that coefficient has to be positive. That's the positivity of the shear viscosity. Okay. Similarly, the only scalar was the expansion. It's multiplied, that expansion term here is multiplied by the expansion, so the bulk viscosity has to be positive. What's more interesting is what happens here. Okay, what's more interesting here is what happens here. Okay, what happens here is that j mu dis by symmetry could have been, let's stick to parity even for a moment, could have been any linear combination of these three vectors. But the term that multiplies it is just one of those three. So what's the nature of that quadratic form? If we call this first, if we schematically denote that first, I'll keep this on. That first vector, that Einstein combination by x. Forget all about index structures and so on. They're not important in the argument. If, say, j was equal to, let's say, alpha 1 times, I'd call it sigma. So sigma times x plus alpha 1 times y plus alpha 2 times z, where x, y, and z are these three vectors. So del dot j was equal to sigma x squared plus alpha 1 xy plus alpha 2 xz. Okay, so we are going to demand the positivity of such a quadratic form. Now, this quadratic form can only be positive if alpha 1 and alpha 2 are 0. Why is that? In order to say that, let me write this as sigma times x plus alpha 1 by 2 y plus alpha 2 by 2 z, the whole thing squared, minus sigma alpha 1 squared by 4 y squared minus sigma alpha 2 squared by 4 z squared. And then there's this xy term. There's the xy term as well, right? I'm sorry. I should write it as, I should write it as minus sigma alpha 1 y by 2 plus alpha 2 z by 2, the whole thing squared. Okay. Now, remember, quadratic form is positive definite if it's positive for every conceivable value of the variables. Now, let's choose our variables so that this term vanishes. We choose z, solve for z as a function of x and y so that this term vanishes. This term is now negative definite. Okay, so this quadratic term here, this quadratic form here is not positive definite unless alpha 1 and alpha 2 individually vanish. You can say this more intuitively. You know, the key point here was that there was no y square term and z square term in this quadratic form. Okay, because of this, no matter what you choose x to be, if you choose x to be anything fixed, I can always choose y to be big enough and of the wrong sign so that this term will drive this thing negative. Similarly for z. So Landau-Lifshitz argue from here. Therefore, positivity of the entropy current imply alpha 1 is equal to alpha 2 is equal to 0. And therefore, the parity even considerations that we have obtained from before, okay, follow. And this is very simple. Okay. Now, however, let's try to take this reasoning and see if we can recover parity odd results. Please.
Are you using Landau gauge?
What? I'm using Landau gauge here, yes.
But so the second term in JS isn't that 0 in Landau gauge, so you wouldn't even have
this one? Yes. So these two expressions were frame invariant, applied to every gauge. From here on, I specialize to Landau.
So, but then the last line, you've got two terms that come from differentiating the term that would be 0 in Landau gauge.
In the last line, you get two terms. You see, both these expressions are true in every frame. Then whatever you get, you know, what you would have got from here, you say, how would this work out if you just start with, now, you know, part of this pi mu nu comes not from the fact that it was here, but by using the fluid dynamic equations of motion. Okay, you use conservation of the stress tensor in this argument. Okay, so it's even in Landau gauge, it's true. You could just have set this to 0, but in Landau gauge, you would have just got this result. I could show you in more detail. Go. Okay, excellent. Fine. So now, suppose we try to do better with this thing, with this way of reasoning. Suppose we try to argue try to understand what happens for parity odd fluids. In particular, let's assume that there is a U1 cube anomaly in our system. Okay? Suppose there is a U1 cube anomaly in our system. Then we could try to do as Landau and Lifshitz suggested. That is, we could try to take their entropy current, compute its divergence, and see what you get. Now, when you do that, it turns out that there is an extra term in the divergence of the entropy current coming from the anomaly, and that extra term is proportional to F wedge F, or E dot B. Now, this E dot B term is precisely the kind of term in a quadratic form that is not positive definite, because there's no E squared term, there's no B squared term, but there's this cross term that's not positive definite. So, if you use the Landau-Lifshitz entropy current, you would conclude that in a system with an anomaly, there is no way that entropy positivity can be maintained. Systems with anomaly appear to violate the second law of thermodynamics, even at least locally. And this sounds like a big puzzle. Okay, this sounds like a big puzzle. Also, you would conclude that any system which had non-zero terms for the parity odd coefficients in hydrodynamics, by the same reasoning, would give you a non-positive entropy current, and this you might use to conclude that these terms were just zero, which is what everyone I think had previously done. Except that about 2 or 3 years ago, we did a calculation in ADS-CFT using the fluid gravity map, which I will spend the next 2 lectures describing to you, and we found that these parity odd coefficients were not zero. Okay. So when we did that, Son wrote us an email saying, look, your calculation looks very interesting, but it can't be right, because it violates the positivity of entropy. Look at Landau-Lifshitz. Okay, and this led to this interesting story that I will now review to you in parts, firstly just from the fluid dynamics side and then from the gravity side. Okay, so what's the resolution? Well,
To be fair, I don't know the history of, but Landau-Lifshitz just postulated this entropy current. They certainly allowed the possibility of corrections to the entropy current if you consider other processes. Is there a resolution there or no?
Yeah, that is the resolution. That is the resolution. That is the resolution. Absolutely. So there is a small modification of this procedure, as you mentioned, that will get things right, as I'm now going to describe to you. Okay, and that modification is let's not use intuition to assert the form of the entropy current. Let this entropy current be free. That is, let's choose the entropy current to be the first order entropy current, what we call in our papers the canonical entropy current, plus an arbitrary first derivative correction to this entropy current. Okay? And we will fix this entropy current along with the transport coefficients, okay, in a way so as to ensure positivity of entropy. Okay? This, in a particular context, is what Cern and Sirocco did. Okay? And going through this process, which is something I would have loved to do, but I don't have the time for, going through this process is very illuminating. Okay? When you go through this process, you allow for the most general arbitrary entropy current. Okay? Compute its divergence. Compute its divergence, and you get various terms. You see, unlike for the canonical entropy current, you get a quadratic form, and then in addition to that, you get a term that's linear in second order data. Okay? Terms linear in data cannot be positive definite, so you demand that the coefficients of those terms are zero. That constrains the entropy current. Okay? The quadratic form that remains then must be positive definite, and you put all the kinds of constraints we were talking about before. And when you do that, you find something interesting. You find that you get the parity even part of the entropy current is bang on constrained to be the Landau-Lifshitz form. So if you start with the most general possibility and impose all the positivity restriction, it bang on constrains the parativity even part to be the Landau-Lifshitz form. So that was good. However, it allows parity odd corrections to the Landau-Lifshitz form, and putting those parity odd corrections, which are actually tightly related to the velocity corrections that we had up here. There's a tight relationship between the parity odd corrections to the entropy current and these parity odd corrections to the velocity configuration in equilibrium. When you put that into the equations, the positivity amounts to a set of differential equations. A set of differential equations on these parity odd coefficients. You solve these differential equations and you obtain a solution with two integration constants. Okay? You solve these differential equations and you obtain a solution with two integration constants, and the solution turns out to be exactly this object, where this is of course the anomaly coefficient, and the two integration constants are, remember where was C1 and C? Oops. Okay. C1 and C2. Okay, so you get an almost perfect, but you know the other integration constant, this guy that we call C0, where's that? This guy here does not appear from that method. Okay, so we get an almost perfect agreement between these two results with a mismatch of one constant. Okay, with a mismatch of one constant, and you might wonder what's going on with that one constant. Well, actually, there's a clear understanding of what's going on with that constant. Okay, you see, in the method that you use for demanding entropy increase, you most naturally require that the entropy current be a gauge invariant object. Okay, but if you think about it, there's no particular reason that you should have a gauge invariant entropy current. You see, because the entropy current outside equilibrium is not necessarily physical. What is physical is entropy production, because in any process you can measure, suppose you have a flow from equilibrium to equilibrium, you measure the initial equilibrium, you measure the final equilibrium, the difference between these is physical. So you must deal with entropy currents such that their divergence is gauge invariant under ordinary U1 gauge transformations. But it's not clear to me that you're forced to deal with processes which actually have a physical entropy current itself. Okay, it turns out that compared to the Sohn-Soroka argument, that allows you to add one more term in the entropy current, which is star of the Chern-Simons form, ADA. If you add star of ADA, allow for the further generalization of this of the Sohn-Soroka kind of entropy current with the star of ADA, you get a perfectly gauge invariant expression for the production of entropy, and the additional freedom that allows introduces one more constant in the differential equations, which matches with the C0 exactly. Okay, so when you allow yourself maximal possible freedom in dealing with the entropy current, put no more restrictions on it than are required physically. Okay, at least in this example, you get exactly the same constraints. You know, this whole process, the entropy current process, gives you inequalities only on the non-dissipative terms, and it matches exactly with what you get from the equilibrium analysis. We've checked this in this case. We've also checked it at second order for uncharged fluids. You know, these 5 equations that you get from equilibrium analysis exactly match what you get from doing an honest entropy current analysis, though that last process is much more difficult. And we've checked it in first order parity invariant hydrodynamics in 2 + 1 dimensions and 1 + 1 dimensions. So, in several examples, admittedly at low orders in the derivative expansion, these two processes agree completely in the equalities. Of course, the entropy production method also gives you inequalities that, as we discussed, the equilibrium method is blind. Okay. So, there are at least, so I'm almost out of time, there are at least, just to summarize, there are at least two different methods, two different physically reasonable constraints that one can impose on the constitutive relations of hydrodynamics. The first one is that it agree with general expectations of equilibrium. The second one is that these equations are consistent with a local form of the second law of thermodynamics. Okay? The equalities that you get in every example that we've computed from these two methods turn out to be the same. Okay? The first method is blind to the inequalities. Okay. So, I think it's a very interesting question to know whether this is just a coincidence of low numbers or whether it's generally true. Can we prove that all the inequalities, all the equalities that you get from the entropy positivity method are the same as those that follow from equilibrium? In other words, can we prove that if a system has fluid dynamics that is consistent with equilibrium, then you can write down for that system an entropy current which is positive definite, provided that the coefficients obey certain inequalities. In other words, can you prove that a system that obeys entropy positivity, a small deviation of that system in a method that agrees with equilibrium continues to obey entropy positivity? Because if an inequality is obeyed, a small deviation can't change that. Okay? If you can prove that, this sounds independently interesting to me just in the study of hydrodynamics, forgetting about gravity for a moment. It sounds independently interesting to me because it relates a sort of deep idea, this increase of entropy, to something much simpler, apparently much simpler, namely a pedestrian idea, namely that equilibrium should be established. Because, okay, we don't have such a proof, neither do we have a clear counterexample to this claim. I think it would be very interesting to understand the connection between these two things and perhaps other physical constraints, some of which we are in the process of exploring, to get a whole picture of this. I just end with one last statement about this. Where you see, just to get the logical structure of what we're trying to do in our head, suppose you were dealing with an ordinary kind of classical mechanical system, and you hadn't realized that classical mechanics or fundamental equations in the real world always come from an action. You just started writing down equations of motion. You would find just the claim that these equations of motion come from an action, any action, significantly constrains possible forms of equations of motion. Okay? There's an integrability constraint, for instance. The one equation of motion is a derivative of the same object with respect to one variable. The other equation of motion is a derivative of some other variable. You take the cross derivatives, they must be equal. This is not true for arbitrary equations of motion. The fact that they come from actions greatly constrains the structure of equations of motion. Okay? So, there is a beautiful principle for fundamental physics, namely all equations of motion must come from an action. Now, in hydrodynamics, the way that it's traditionally formulated, we're not working in terms of actions. We're working in terms of equations of motion. But what we're finding is that there are constraints roughly of the nature that these equations of motion are constrained because they have to agree with something else, morally because they must agree with somehow with some sort of equivalent of an action. So to completely understand the structure of the equations of hydrodynamics, I think, would be to find the beautiful version of that, the analog of that statement, which was these equations come from an action. That was what I would consider a solution to the problem of what are the allowed equations of hydrodynamics. Okay? These words I can't make precise at the moment, but just to give you a sense for what was this. Okay. So this basically ends my lectures on the structure of the equations of hydrodynamics as they are understood to my knowledge today. I emphasize there's a lot to do. It's such a basic and fundamental subject in the study of physics, and it's so ill understood in a structural sense. Okay, and so this is really fascinating. But what makes it, to me, 10 times more fascinating is that this connects with basic and fundamental questions in the study of gravity, and that's what the next 2 lectures will be about. Okay, thank you.
Questions for Shiraz?
So if in the entropy current you can just add terms that are just constrained by symmetry, for example, or like, why is it an entropy current? Because it's some current that has a positive divergence, but that to leading order agrees.
Good.
And it's not like, how can you make sure that it's true to higher orders, I think, which is one of the questions you.
Okay, let me address the first question first. You see, this goes back again and again to the question, what do you mean by a thermodynamic quantity out of equilibrium? In equilibrium, the notion of entropy is extremely well defined. It's some derivative of a partition function. Partition function is trace over a Hilbert space, we know exactly what that means. Okay? Out of equilibrium, the notion of entropy, and in particular the notion of local entropy, is not well defined. Okay? If you want to count the number of states that live in a certain volume, what does that mean? Wave function spread outside that volume. Okay? This is something that is actually well defined as entanglement entropy. That's always well defined. But the notion of local entropy has no absolute God-given meaning, as far as I know, out of equilibrium. So, an entropy current for me, as far as I'm concerned, is simply the following object. It's any object that agrees with the absolute notion of entropy in equilibrium and is positive divergence for an arbitrary process. What does it buy you? It buys you the ability to prove the following theorem, that for any flow from equilibrium to equilibrium, entropy always increases by using Gauss's law. Okay? So I don't think you should give more meaning to the entropy current than that statement. That's the statement that in a flow from equilibrium to equilibrium, entropy must always increase. Now there's a very interesting question. I don't know, there's this question that it's not, maybe it's obvious, but I've never managed to completely convince myself of the claim that this requirement, which is I think the physical requirement, that from equilibrium to equilibrium entropy must always increase, requires the existence of a pointwise positive divergence. I mean, surely if there's a pointwise positive divergence entropy current, that second statement is true. But it's not so clear to me that the other one is true. It's not clear that it's not. Okay, but certainly, if it's true, it would imply this. Okay, yeah.
I mean, you could have one patch that's like, whose entropy is decreasing at the expense of like stuff surrounding it, and the overall thing is still positive, right? That's what
you could have production here. Yeah. However,
there's a concept of local equilibrium.
Yes.
That's really the key thing.
Yeah. And the equations of hydrodynamics are local, and moreover, you're allowed to add arbitrary local sources. Suppose it was going to happen that destruction here would be modified by production here in a particular flow. Well, let me change the flow a little bit by changing the source to prevent that from happening. I mean, I don't think it would be easy to get arbitrary processes, having entropy increase without it happening locally. But I don't see a theorem saying that either. In this game, one should be careful, I feel, because there have been mistakes before. And it's possible that there's subtleties. Yeah.
But there are systems like if I just isothermally compress a gas, the system's the environment entropy increases and the gas is decreasing. That's a perfectly valid.
Yeah, you see, I'm not saying that the entropy of any given stuff should increase. The statement is that the divergence of the entropy current vanishes. Okay, in order to understand this, let's look at a case where the divergence of charge current is 0. This is we've got a charge. Divergence of charge current is 0. That doesn't mean that the charge in any given region can't decrease. It means that the decrease should be compensated by the flow out. Okay? So the kind of example you're talking about is not in conflict with the paucity of divergence. In the kind of situation you're talking about, entropy in a region decreases because some of it is flowed out. That's fine. We're talking about production. We're talking about the difference between the decrease here and the flow out. That should be positive. That's the claim. It's a more subtle.
Yeah.
Okay. Yes.
So, can you use any notion of entropy as counting microstates in this? I mean, so you want to give some notion of entropy beyond just some thermodynamic thing? Can that make sense? Or
yeah, I don't know how to do that in the local way. Suppose you've got microstates. The exact wave function of your system extends across regions. You want to give a local notion of entropy. Maybe you can, but I would love to see it done precisely. I haven't come across a useful notion. The entanglement entropy is a very precisely defined notion in a field. Okay, it's very precise because you've got degrees of freedom that are associated with regions in space. You take your Hilbert space, break it up into two different Hilbert spaces, blah blah blah. You have a very precise notion, but we're not talking about entanglement entropy. Yeah. Yes.
Is there any experimental consequences of the new transport coefficients you found?
Yeah. Well, probably not. Probably not, because of something that I have not had the time to tell you about, and that is that there are additional constraints from both in the entropy increase method and in the method that we discussed from imposing additional discrete symmetries. And the additional term that we're talking about is killed by CP invariance, possibly also by CPT invariance. So I think that this term, if you impose additional discrete symmetries that are likely to be true in realistic systems, is probably just never there. Okay, I doubt that this term has experimental consequences for this reason. Okay, but I think it makes a conceptual point that in dealing with the entropy current, you should allow yourself more freedom than you would otherwise. So, but my answer is probably not. I'm not 100% sure, but probably not. Yes.
So in reality, transport coefficients are not necessarily a constant. For example, conductivity can be a function of the electric field, and shear viscosity can be a function of the gradient of the velocity.
Yes.
So do you have any idea to formulate, the fluid dynamics of that kind of situation? Non-Newtonian version of the fluid dynamics.
Okay, so function of the we are allowing, of course, the shear viscosity to be a function of temperature and chemical potential. And we allow only those because we are allowing only terms that are zeroth order in the derivative expansion. Yes. Now, if you have the shear viscosity as a function of an electric field, the way we would work, because we're treating all derivative terms as small, and the electric field is a derivative term, it accelerates things. Right. Okay, what we would do is to take that object and expand it, and count, the first order in the expansion in this electric field as the second order coefficient, and the term as a third order coefficient. So that's not the way we
so if
think.
we could make a resummation, then perhaps we can reproduce.
Yeah. It may be that there's something useful. It could be that there's, for instance, as you indicate, the magnetic field, for instance, is sort of special because it allows for equilibrium. Even if it's fast varying, it allows for equilibrium. So there's some sense in which some terms, even though they have derivatives, should be treated differently from others and maybe resummed. That sounds interesting, but we've not tried. That sounds interesting, but I don't know how to do it. But it sounds interesting.
Okay, let's thank Shiraz for a very nice talk.